Alright, as we get ready to start doing some serious machine and frame analysis, we need to make sure that we've got the free body diagrams well understood. Now, everybody will tell you, of course, that the most important thing is a free body diagram and it being correct, and that's ever so true here with frames. It almost becomes trite because everybody knows that it's important, but typically people say, yeah, you're always saying things like that. Well, it truly is the case here. And so we're going to do a couple warm-up exercises, this being one of them. Right now, one of the things you have to be able to do in the analysis of frames and machines is be able to correctly figure out how many members are in the system. So we've got two here, ACD and BCE. Now you're used to in trusses just going from joint to joint, and you might think we've got 1, 2, 3, 4, 1, 2, 3, and 4 members, and that's just not the case. If we did, this thing would not be stable. So you have to be able to visualize, interpret the drawings, one long member, another long member, and they're just simply pinned together at point C. And that's a crucial thing here, that at point C then we're going to have a pin, and that means two forces. And I haven't shown any arrows here on those. I've just simply indicated that, well, there's something there. Right now we've got frictionless surfaces, so here at D, that means that wall is going to push back, and there's no frictional force, only a normal force here at D. At A, then, again, we have a frictionless surface, so perpendicular to the horizontal means there's only an AY. Now, when you find one of these forces, you want to immediately show them on another free body diagram if they show up, and they don't. Right? This ACD only shows, or A and D only show on ACD. They don't show down here on BCE. Right? B has a pin support, so that would be 2 points of contact, or excuse me, that would be two independent reaction components. Again, I haven't figured out what direction anything is going. And then we've got this 50-pound applied force right here at E. Right, so now let's start figuring out what might be going on. If we were to some moments about point C note that AY would be shown to spin the system in a clockwise direction, dx would try to spin about C in a counterclockwise. That's good. That means those two can be possibly in equilibrium with each other from a rotational standpoint. From a translational standpoint, if I've got dx, the wall, pushing back on D, that means Cx has to be going to the right. And again, as soon as I figure out one of these, I want to immediately show the other one down here on the other free body diagram. Same force, but those are internal effects. So when I put the pin back in, then those things have to disappear. You might say, what do you mean put the pin back in? Well, here's our pin, and this force right here, that's the force of the pin on ACDs. That means ACD is doing the opposite to the pin. So that one would go with this one, and then this one would be, well, we'd have to put that into equilibrium, equal magnitude, opposite direction, and those two would go together. Right? So when we slide that pin back in, everything vectorially disappears. Now back to ACD. Sum of forces in the Y, CY has to be going downwards to equilibrate AY, and as soon as I find that, then I want to show it flipped over onto the other free body diagram down here on BCE. This is crucial that these are equal opposite. They represent the same thing, but the effects on different bodies. Right? And again, the way that would work, this CY going down would be one going up here, and that would need one going down, which creates an upwards one here. Right? And then we get the BX and BY part. Now, BX is easy. It has to be going to the right to equilibrate CX, and then it's not really very easy to tell from the overall situation. You can't tell by magnitudes. Well, without magnitudes, you can't tell for sure. My intuition says that BY is probably going up, given the overall situation. Those are the two free body diagrams that we need to be working with, and for the most part it is. Now, the other thing you might consider is that we actually have a global free body diagram that we could play with as well. I don't usually superimpose them on top of the drawing, but for simplicity here and keeping everything on the same page, I'm going to go ahead and do that. And notice that 1, 2, 3, 4, we got 4 unknowns, only 3 equations of equilibrium. It's the fact that we can pull this apart and have no rotational resistance happening, no friction here at point C, that is going to give us the additional piece of information that allows us to solve for all of these. Right? That's kind of an interesting little piece. So what we could do is some moments about point B, and we'd find a relationship between A, Y, and dx, including the load would get in there, and then you go to ACD, some moments again now about point C, and get another relationship between AY and dx, 2 equations, 2 unknowns. You could then therefore solve for both of those, and once you have those, you can find CX and CY, from which then you can find BX and BY, or once you have those, you could come back to the global free body diagram to find the other 2. Notice here, to find anything, we have to go through the bits and pieces and connect them all together, right? And we'll be doing that in other ones. This exercise is just mostly about the free body diagrams and a little extra value added of thinking ahead to the equations of equilibrium that would come from these and how we might begin to use them.